section 4.1 to section 4.5. Let us review these sections first. The three concepts are very important. We must know what they mean. A variable, the complement, and literal. In Boolean algebra, a variable only has two values, 1 or 0, and also the complement. A literal is a variable or the complement. Associative laws, and we have learned Boolean addition, Boolean multiplication, and commutative laws, associative laws, distributive laws, and 12 rules of Boolean algebra. 12. The last three rules must be remembered by yourself. 10, 11, and 12 rules. The 10 rules is A or AB equals A. A or AB equals A. And the 11 rules, A or A bar B equals A or B. The symbol or can also be called plus. The 12 rules, A or B and A or C equals A or BC. We must remember the three rules. Then section 4.3. Section 4.3. De Morgan's theorem. It has two forms. One form is x, y bar equals x bar or y bar. Also, x, y, z bar equals x bar or y bar or z bar, and so on. The second form is x or y bar equals x bar and y bar. Also, x or y or z bar equals x bar and y bar and z bar, and so on. That is the text of De Morgan's theorem. Substitution theorem is also very important. Each variable in De Morgan's theorems as stated can also represent a combination of other variables. For example, x can be replaced by a b or c. Y can be replaced by a or b and c, and other combination of variables. Then we have learned section 4, Boolean analysis of logic circuits. First, we must get the Boolean expression for a logical circuit. And the method is begin at the input, or the leftmost or the upmost, and work towards to the final output. So we must write each gate's output, and then write the final output. So for this circuit, we must first write this output, and then write this output, and then write the last output. Also for this circuit, we first write the AND gates output, AB bar, and then AB bar and C bar. Right. And then write the output of this gate, C bar and B, and then the last output X equals AB bar and C bar, or C bar B, The second potential is constructing a truth table for a logical circuit. Truth table. The second method. Truth table. If we know the logic expression of a circuit, we can construct the truth table of this circuit. First, we know the expression is A and B or CD. So we first list all the variables first as the inputs, and then write each output of the gate, for such as x1, x2, and then the last column is the final output, x3, and the value of the input variables must be write down from zero to the maximum value, from the minimum value to the maximum value. For variables, the minimum value is 0, and the maximum value is 15. 15. So there are 16 different combinations for 4 variables. And then first, evaluating the expression. It is a little complicated, but we can, in fact, we can write down each combination of the 4 values, and then find out the output value. For example, if we know A, B, C, D, equals 0, 0, 0, 0. Then we replace these values to the expression. 0 and any value equals 0. So x3 is 0. And then ABCD equals then ABCD equals 0, 0, 1. Then also A equals 0, so the value of x3 is 0. Only when A equals 1. 0, 0, 0, 0. Only when A equals 1, the output can maybe 1. So when A equals 0, the output is 0, 0. So the first A combination equals 0, and then the last A combination is 1 and 0. 1. 0, 0. And the last is right. A equals 1. So we only need to decide what is the value of this expression. B plus C and D. So 0 plus 0 and 0 equals 0. So the answer is 0.
Also
0 plus 0 and 1 equals 0. Equals 0. And 0 plus 1 and 0. 1 and 0 equals 0. 0 plus 0 equals 0. So is 0.
1. This answer is
0 and 1 of 0 plus 1 and 1. 1 and 1 equals 1. Equals 1. And plus 0 equals 1.
Yes.
So the output is 1.
Then
1 B equals 1. 1 plus 0 and 0 equals 1.
yes.
Right?
Yes.
Equals 1. Also, the last also.
This is also 1.
If B equals 1, the output is 1.
1.
So
1, 1, 1.
1. This is the other method, the second kind of method to constructing all truth tables. If you find that this method complicated, and section 4.5, we have learned simplification using Boolean algebra. It is really hard for us. simplification means reduce a particular expression to its simplest form. The simplest form. What is the simplest form? Use the fewest gates possible to implement a given expression. Fewest gates. Because the gates can be AND gate, OR gate, inverter, and AND gate, OR gate. So the result is not the only one. Maybe has several results. The first example is this. We have learned AB plus A and B plus C, and B or B and B plus C. According to the attributive law, A and B plus C equals AB plus AC. So then BB plus BC.
B plus BC.
BB equals B. BB equals B. And B plus BC equals B. AB plus AD equals AD. B plus BC equals B. Then AB plus B equals B. So the last simplest form is B plus AC. B plus AC. If we use two kind of circuits to represent this expression, the first circuit is about the original expression. The original expression. It has 5 gates. 2 OR gates and 3 AND gates. But after we have simplified this circuit, this expression, the circuit only has 2 gates, 1 AND gate and 1 OR gate. Example 4.9. Simplify the following Boolean expression. A little hard. First, according to the distributive law, we know that this expression can be written as AB bar C plus AB bar BD. Right? And A bar, B bar, and C. Then we know that B bar and B equals 0. Right? B bar and B equals 0. Because the value of B and B bar are inverted. If b equals 1, then b bar equals 0. If b equals 0, then b bar equals 1. Right? So we can write like this: a and 0 and b plus a bar, b bar, and c. Then we find the two terms have common factor, b bar. So we can a b bar c plus a bar b bar equals what? A b bar c. What?
No, we have another, right?
Yes.
Yes. C.
According to the distribution law. A b bar c and c plus a bar b bar c, right? And this term c and c equals c, so it equals a b bar c plus a bar b bar c. Then the common factor is b bar c. So
A plus B bar equals
yes, a plus a bar
equal 1
and b bar c. Because a plus a bar equals 1. So the last form is b bar c. Only one gate, and gate. And
okay, how about 0? A multiple 0 multiple B.
which line? This
Second line.
second line.
After that line. 0 dot A dot D equals 0.
0 and a equals 0. You know? Because if a equals 1 and 0 equals 0. If a equals 0, 0 and 0 equals 0. Example 410. Example 410, there are two kinds of methods to simplify the following Boolean expression. We have learned. Using the 12 rules and the three different Boolean laws. The first method, this expression we find that this term and this term has common factor, BC. So they can be written like this: BC and A bar plus A. Right? Right? A bar plus A. And then A bar plus A equals 1. So it equals BC and 1. Then AB bar C bar and AB bar C also have common factor AB bar. So they can be written as AB bar and C bar plus C, right? Right? C bar plus C. So C bar plus C equals 1. So it equals A B bar and 1. And A bar, B bar, C bar. Then A B bar and 1 equals A B bar. Equals A B bar. So we also find that A B bar and A bar, B bar, C bar have common factor B bar. So the B bar is the common factor. Then they can be written as B bar and A plus A bar C. A plus A bar C bar, right? Plus A bar C bar. And A plus A bar C bar equals A plus C bar, right? Rules 10. Rules 11. Rules 11. So it equals this. Equals this. And then, according to the distribution law, we know that this expression can be written as A B bar plus B bar C bar. B bar C bar. This is the first simplest form. The first simplest form has the circuit. The circuit has three AND gates, and two OR gates. The second form, we find that B bar C bar, the second term and the third term have the common factor B bar C bar. So they can be written as B bar C bar and A plus A bar. A plus A bar. Then this term have common factor AC. So they can be written as AC B bar plus B. B bar plus B. So we know that A plus A bar equals 1. B bar plus B equals 1. So it can be written as B bar C bar plus AC. And then we know that the first term and the third term have the common factor C. So they can be written as C and A bar B plus A. A bar B plus A. And then we know that A bar B plus A equals A plus B.
Rule 11.
So at last it can be written as B bar C bar plus AC and BC. It is the other simplest form for this expression. It also this circuit it also has 3 AND gates and 2 OR gates. But it has 1 inverter, 2 inverters, and it also has 2 inverters. So they are equivalent, and also they both the simplest form. Example 11. Simplify the following Boolean expression. AB plus AC bar plus A bar C bar C, A bar B bar C. Then, according to the De Morgan's law, we know that it can be written as AB bar and AC bar, right? Then this curve AB bar equals A bar plus B bar, right? And AC bar equals A bar plus C bar. And then A plus B bar and A bar C bar. A bar plus B bar and A bar plus C bar equals A bar and A bar. A bar and A bar plus A bar and C bar, right? And plus B bar and A bar, B bar and A bar, and then plus B bar and C bar, right? Then A bar and A bar equals A bar. A bar C bar, B bar C bar. Then A bar B bar plus A bar B bar C equals A bar B bar, right? And this A bar B bar is the common factor, right? A bar B bar. So these two terms equals A bar B bar. because A bar, B bar equals A bar, B bar, right?
Yes.
1 plus 3 equals 1. Equals 1. And then A bar plus A bar C bar also equals A bar, right? A bar because A bar and 1 plus C bar equals A bar. Equals A bar. So it equals A bar plus B bar C bar and AB. Then A bar plus A bar B bar also equals A bar. Also equals A bar. So the last simplest form is A bar plus B bar C bar. So the circuit has one AND gate and one OR gate.
Yes, sir.
Also, it has 3 inverters.
Not gate.
Inverters, not gate. Right. Then we will learn sections 4, 6, or 6. Standard forms of Boolean expression. Standard form. What is the standard form? The first standard form is the sum of products form. The sum of products form can be abbreviated SOP. SOP. Sum of products. Sum of products form. So we must know what is all product term. 2 or more product terms are summed by Boolean addition. The resulting expression is a sum of products. For example, this term is all product term, right? This term is also all product term, A and B and C product, and is equivalent multiply. And is equivalent to multiply. So we can call this term product term or product term. This is also all product term. This is also all product term. Also all product term. If we find that 2 or more product terms are summed by Boolean addition, or by all Boolean addition, that is the OR gate. Then the resulting expression is all sum of products form. Sum of products form. So this expression is all sum of products, and this expression is also a product term. But we must notice that first, on SOP expression can contain a single literal term. For example, A is also can be regarded as a product term, right? Also can be regarded as a product term. So this is also OSOP, sum of product form. And this is also A bar can also be regarded as a product term. The second, a single over bar can extend over than one variable. For example, this expression cannot be regarded as SOP because the over bar extends over than one variable. So, if the expression is A bar B bar plus BC plus A B bar, then it is OSOP. But this cannot be regarded as OSOP. Understand? Over can extend over one variable. The third, more than one variable in a term can have an overbar. For example, two variables have overbar, right? Two variables have overbar. Domain for Boolean expression. Domain means that the set of variables contained in the expression in either complemented or uncompleted form. Domain. For example, A bar and B and B bar and C bar. This expression, the domain is the set of variables A, B, C. And this expression A, B, C bar plus C, B bar, E plus B bar, C, E, B bar. What is the domain? How many variables in the domain?
5 variables.
5.
A, B, C, D, E.
Please note this expression. This contained in either complemented or uncomplemented form. So there are
3 variables.
One, two, three, four, 5.
5 variables.
5 variables. Because it is all not n.
Yes.
So
Uncomplete.
So the domain is the set of variables A, B, C, D, and E, 5 variables. Implementation of SOP expression. This example, AB plus BCD plus AC. This is a two input AND gate.
Yes, sir.
And this term is three input AND gate. And this is two input AND gate. AND gate.
3 and 2 or gate.
And yes, three input OR gate. Three input, one input, two input, and three input. So implementing OSOP expression simply requires ordering the outputs of two or more AND gates. AND gates. So we must know that a product term is produced by an AND operation, and the sum of two or more product terms produced by an OR operation. So we can know the circuit for this expression. The circuit for this expression is like this. First, we list the AND gate. The first AND gate is A and B, and the second B and C and D, and the third A and C, right? Then use the OR gate. So the output of this circuit is AB and BCD, AB plus BCD plus AC. Also, this expression can also be written as like this. AB plus BCD plus AC. These two kind of circuits also represent this expression.
Not.
Yes.
Yes, sir.
Yes.
Same.
NAND gate. Three NAND gate and one NOR gate.
Same.
The circle can be in front of this in the input of this OR gate or the output of the OR gate. AB bar plus BCD bar
AC bar
plus AC bar. Right?
the same expression.
The expression of this circuit is this one.
Yes.
Then we know that according to De Morgan's law, De Morgan's theory, we know that this one.
So AB double bar.
Plus. So it equals
AB double bar.
AB bar and
BCD bar.
BCD double bar and
AC double bar.
AC bar.
So AB dot BCD dot AC.
So equals AB plus and BCD and no. No. Right? Because this is on inverter. This is also on inverter. So there must be double one.
So AB plus BCD.
Double one. So it is equivalent to this. But this
No, this one is not set.
this AB bar, the right circuit is this example is AB plus BCD plus AC, and the right circuit first we know that it is AB bar, BCD bar, right? AC bar. NAND gate. So we know that NAND gate they are AND, right? Like this. So it, according to De Morgan's law, we know that it is equivalent AB double bar plus BCD double bar plus AC double bar.
So AB plus AC.
Yes. Same. So the three circuits are equivalent. This one, the second one, and the third one. But there are different gates. The gates are different.
But same
Right.
output.
The first circuit has AND gate and OR gate. The second circuit has NAND gate, an AND gate, and NOR gate. And the third circuit has NAND gate.
And NAND gate.
Only one kind
Of gate.
of gate. NAND gate. Okay, have a rest for 10 minutes. We can use C plus C bar equals 1. So A plus 1 and 1. It is equivalent. Then 1 equals C plus C bar. Right? 1 equals C plus C bar. Rule 6. C plus C bar equals 1. And then according to distributive law, it equals AB bar C plus AB bar C bar. Then the last form is the standard SOP form. The second step is repeat step 1 until all resulting product terms contain all variables in the domain in either complemented or uncompleted form. For example, if the domain contains 4 variables A, B, C, and D, then A, B, C, and D. A, B, C, and D. Then A, B bar, this product meets C and D. Meets C and D. Meets C and D. So we must first add C to this term. Add C to this term like the first example, the last example. And then this term, D is missed. So we must continue to add C. A, B bar C, B plus B bar. A, B bar C bar, B plus B bar. Then according to the distributive law, we know that it equals A, B bar C, D plus A, B bar C, D bar plus A, B bar C bar, D plus A, B bar C bar, D bar. So there are four product terms, and all the product terms include four variables. This is the method how to convert a non-standard SOP form to standard SOP form. Then binary representation of a standard product term. Binary representation. All standard product term is equal to 1 for only one combination of variable. For example, if A equals 1, B equals 0, C equals 1, D equals 0, the product term has a binary value of 1, 0, 1, 0. 1, 0, 1, 0.
A equal 1, B equal 2, so on, 0.
So A, B bar, C, D bar equals 1. Right?
Yes.
Right?
B bar equal 1, C bar equal 1.
Because it equals 1 is equivalent to A 1, B bar 1, C 1, D bar 1. Right?
Yes, sir.
And then we know that if B bar equals to 1, then B equals 0. If D bar equals 1, then D equals 0. So the product term has a binary value of 1, 0, 1, 0. All SOP expression is equal to 1 only if one or more of the product terms in the expression is equal to 1. Only one or more product terms. If any product term equals 1, then the SOP expression is equal to 1. For example, for 14. Determine the binary values for which the following standard SOP expression is equal to 1. This standard SOP expression. If this expression equals to 1, then we know that ABCD equals 1. ABCD equals 1. So we can find that A equals 1, B equals 1, C equals 1, D equals 1, and then A, B bar, C bar, D equals 1 is equivalent to
A equal 1, B bar equal 1.
A1, B bar 1, C bar 1, D equals 1. So D equals 0, C equals 0. Also, the third third product term.
ABCD equals 0.
Yes, yes. A bar, B bar, C bar, D bar equals 1. So, A0, B0, C0, D0. So, if one or more standard product terms equals 1, then the expression is equals to 1. Is equals to 1. So if A, B, C, D equals 1, 1, 1, 1, or 1, 0, 0, 1, or 0, 0, 0, 0, then the expression equals to 1. Right? Right?
Yes, sir.
Then how to converting SOP expressions to truth tables now? All standard Boolean expressions can be easily converted into truth tables now using binary values for each term in the expression. Then standard expressions can be determined from our truth tables. First, if we want to convert an SOP expression to truth table method, the first step is list all possible combinations of binary values of the variable in a constructed truth table. The second step is convert the SOP expression to standard form. And the third step is place a 1 in the output column for each binary value that makes the standard SOP expression for 1, and place a 0 for all the remaining binary values. For example, develop a truth table for the standard SOP expression A bar, B bar, C plus A, B bar, C bar plus A, B, C. Step 1. List all possible combinations like this: A, B, C, three variables. So there are three combinations. So there are 8 combinations. 8 combinations from 0 to 7. From 0 to 7. 0, 1, 2, 3, 4, 5, 6, 7. Right? And then step 2. Standard SOP expression. This binary value and this binary standard product term, its standard product term is A bar, B bar, C bar. This is A bar, B bar, C. A bar, B, C bar. A bar, B, C. A, B bar, C bar. A, B bar, C. A, B, C bar. A, B, C. A, B, C. So that's 3. We know that the expression is A bar, B bar, C plus A, B bar, C bar plus A, B, C equals 1. Yes. So we can find that there are 3 terms equals 1. It is equivalent or binary representation is 0, 0, 1, right? 1, 0, 0, 1, 1, 1, right? So write down 1. Write down 1 to this position. And the others are 0. The others are 0. So this is the truth table for this standard SOP expression.
So,
if we want to develop a truth table for the standard SOP expression A and B plus C plus CD plus CD, first step we must list all possible combinations A, B, C, D. So there are 16 combinations. 2, 4, 2, 4, 16. There are 1, 2, 3, 4, 5, 6, and 13. Step 2. Step 2. Standard SOP expression. Convert the non-standard SOP expression to a standard SOP form. So we must convert this expression to a standard form. The method is AB. According to distributive law, we know that it equals to AB plus ACD plus ACD. Then AB. We know that AB equals to AB1, right?
yes, sir.
Equals to ABC plus C bar. So it equals to ABC plus ABC bar. Then it also equals to ABC D D plus D bar, right? Plus A, B, C bar, D plus D bar, D plus D bar, and then also it equals A, B, C, D plus A, B, C, D bar. Plus A, B, C bar, A, B, C bar, D, plus A, B, C bar, D bar, right? And then ACD is equivalent to A, B plus D bar, C, D, right? And then it is equivalent to A, B, C, D plus A, D bar, C, D. So there are 1, 2, 3, 4, 5, 6. There are 6 terms.
Yes.
6 terms. But there are 5 terms. 5 product terms. Why? Because we know that we find that A, B, C, D. So A, B, C, D plus A, B, C, D equals A, B, C, D. So there are 5 product terms. 5 standard product terms. And then step 3, ABCD boundary represent binary representation is 1 1 1 1 and 1 1 1 0 1 1 0 1 1 1 0 0 1 0 1 1, right? So we know that there are 5 ones in the output column. 5 ones. 1 1 1 1.
1 1 0.
Yes. 1 1 1 1. And 1 1 1 0. 1 1 1 0 is 1.
1 1
1 1 0 0 1 1 0 0
1 1 0 0.
1 0 1 1 1 0 1 1 is 1. 1 1 1 0. So there are 5 ones, and the others are 0. Determining standard expressions from a truth table. If we know the truth table, then we can also determine the standard expressions. First, list the binary values of the input variable for which the output is 1. And the second step, convert each binary value to the corresponding product term. Variable equals to 1 and complement equals to 0. Then add all product terms of step 2. For example, determine the standard SOP expression from the truth table. Like this. Step 1, we must find list all the binary values which corresponding output equals 1. This 4. There are 4 binary values, 4 kinds of binary values, which corresponding output is equals to 1. 0 1 1, 1 0 0, 1 1 0, 1 1 1. Then step 2, convert to the product term. 0 1 1. The product term is A bar B C and A B bar C bar. A B C bar. Right? A B C. And then step 3, the standard SOP expression is add the 4 product terms. So the output is x equals A bar B C plus A B bar C bar plus A B C bar plus A B C. AC. OK. 下课。Yes. 下课 class is over.
上课。谢谢大家。